Okay, so thanks for the introduction, and again, so thanks for inviting me here. So my talk today's title is called Quantitative Risk Model. So as Yufei mentioned, so my name is Zhang, and I'm a faculty member at the Helmholtz Center. So my general research interests include machine learning security privacy, which is also my main research interest. Also, I occasionally work on social network mining as well as algorithmic fairness. Recently, I also started to work on online hate speech understanding or quantification. Yeah, this is a collaboration with, let's say, Agile Lab. Okay, and today my talk will be assembled with three parts. The first part is called membership inference attack. The second part is called data reconstruction attack in the online learning setting. And the third one is one of our newest work is called link stealing attacks against graph neural networks. So let's start with membership inference. So I guess I do not need to tell you guys that machine learning now is very popular and has been used in many, such as automatic driverless cars, facial recognition, or your IoT devices at home. So on one hand, machine learning indeed makes our life much easier than before. On the other hand, the reason that machine learning models actually achieve such good performance, it is because it uses the high quality data that is being collected at any minute, every single minute of our life. Yeah. However, many cases, the data machine learning models that is used or trained on contain sensitive information. For example, your biomedical data, as well as, for example, even your smartphone keyboard input. Yeah, so if you're using your smartphone, use, let's say, WhatsApp or whatever messenger, you realize that if you use your phone for a longer time, your next word auto models. Yeah. So again, as I said, so this is good because the model become more useful and powerful than before. Our life become much easier. On the other hand, if a machine learning model trained on such sensitive data can leak its training data information, then this will cause actually quite a large privacy threat. So the so-called privacy of machine learning is basically focused on whether you can infer the information of the training data from a trained machine learning model. Yeah. So before we dive into detail about what is membership inference, I will give you a very simple machine learning pipeline. So nowadays, how do you do machine learning? So what you do is you just first get a data set from the internet, and then you open PyTorch or TensorFlow to find your favorite model. And then you use the data you get from internet to train your model. Once your model is trained, for example, let's say it's an image classification model. Once your model is trained, you just test it. Yeah, so you use one image, you throw to the model, and the model will tell you, okay, so 80%, sorry, 80%, this is a panda. Okay, this is a very simple machine learning pipeline. And what is membership inference in this case? Actually, membership inference in this case is very easy. So basically, the goal of membership inference is to infer whether an image is part of the training data set of the machine learning model. Okay, that's it. And what the attacker has actually here in this case is only have the black box access to the machine learning model, and which means he can only use the image to query the model, and the model will only give him the probabilistic output. You can call it posterior probability or prediction confidence scores, but here let's just call it posterior. Okay, and so many of you guys here probably work on security privacy of machine learning. You must hear one attack called adversarial example. Yeah, or in general, some people like to call it adversarial machine learning. That is basically the most popular attack in machine learning security. For machine learning privacy, yeah, the most popular attack is, or the attack of machine learning privacy is membership inference. So what I'm talking about today regarding membership inference is based on our paper published in NDSS 2019. First of all, I have to say that we are not the first one to do membership inference against machine learning model. The first one was done by Shokri with Shmakov back in 2017 at Auckland. Yeah, so I will give a general introduction for how their attack works. So in general, also you assume you have a target machine learning model is trained on a certain data set. Okay, then you assume you have an attacker who has a data set that comes from the same distribution as the target model training data set. So once the attacker has this local data set, attacker split the data set into two parts, training and testing. And then he uses the training data set to train a bunch of shadow models. Yeah. Here, the reason it's called shadow model because they are the shadows of the target model. So what I mean by that? So if the target model is, let's say, a panda cat dog classifier, yeah, your shadow model is also a panda cat dog classifier. Okay, and more importantly, you can also assume that the shadow model share the same architecture as the target model, and you can also assume you shared all the hyperparameters during the training process of the target model. Okay, so eventually, so you're building your own shadow model, which is a shadow or mirror of the target model. So once you train your shadow models, attacker throw all the training and testing data set from its shadow data set to the shadow models to get a bunch of posteriors. Yeah, here the histogram or the posterior figures here is with the pink background actually is the training samples posteriors. Is the blue background is the testing sample posteriors. Yeah, so here the one notion we need to be clear. So what is a member? Member is just all the samples in the training data. Okay, what is non-member? Which is posed in the testing data set. Okay, so you can see that what I'm doing here, or what the attacker doing here, is trying to build the data set for training the so-called attack model. Because your attack model here give you one image. The image can either be a member or non-member. Okay, and the attack model here is also a binary classifier. Since your attack model is a binary classifier, you need a data set to train the attack model. So that's why the attacker here needs to build a bunch of shadow models, use its own training data set, testing data set, generate the training data set for the attack model. So once your attack model is trained, so to do your attack, yeah, because your goal here is really I want to find whether this panda image is the member of the target model. So what you do here is you throw the panda image into the target model. Target model will give you the posterior, and once you have the posterior, you throw the posterior into the attack models, and the attack model will give you this is a member and non-member. So that is the general process for how Shokri's attack works on membership inference. Yeah, and by the way, so if you work on this field, security, privacy, especially privacy of machine learning models, no matter you are doing membership inference attack or property inference attack or I don't know model inversion attack, even model stealing attack, your attack's architecture or your attack models establishment is always more or less like this. You always need shadow models. Okay, another thing I want to emphasize here. So the reason you need shadow model itself, the reason you can use shadow model to generate a data set is because the shadow model is established by you, and you know what is the members and non-members for the shadow model. Okay, so before I go even further, so one reason the membership inference attack is because there is a so-called thing called overfitting. Yeah. So what is overfitting? So I suppose many of you guys here knows about it. So in general, so in a nutshell, if a trained model see a sample that is part of its training data set, the model tends to give more confident prediction on this sample compared to a non-training sample. Okay, non-training sample is non-member sample. Okay, so that's how this attack works. And so far, all I'm talking about here is the attack by Shokri. So in this attack, there are three key assumptions. The first assumption is it assumes the adversary has a data set that comes from the same distribution as the target model data set. The third assumption is they assume the attacker needs to train multiple shadow models as well as multiple attack models. So if you train multiple shadow models, multiple attack models, this indicates the attacker needs more resources. Yeah. So what we try to do in our paper is see whether we are able to relax all these assumptions to make the attack work. If after we relax all these assumptions, make a much simpler attack model assumption, and our attack model can still achieve a similar result, then in that sense, we can say membership inference can be easily done, which further shows the membership threat is bigger than you thought. Okay, so let's dive into detail. So follow these ideas, we go for 3 different attacks. The first attack, we do a very simple thing. So all we did here for the first attack is we just replace multiple shadow models, multiple attack models with one shadow model and one attack model. That's it. All the other parts stay the same. So the experiment results here. So remember, membership inference is binary. Yeah. So and the left is the attack model's precision, and the red figure represents the attack model's requirement. Yeah, of course, higher performance. Our approach is marked as the green bar, while the original attack of Reza Shokri with multiple shadow models, multiple attack models have the blue bar. You can see that for the attacks, both our attacks and Reza Shokri's attacks achieve similar results. What this means is actually the attacker does not need to train multiple attack models as well as multiple shadow models. One shadow model, one attack model, that's enough. But this is a very simple, relaxation. So what really matters here is you assume that you need to get rid of this same distribution assumption. Because here, assumption is too strong. Imagine if you want to attack a model that is trained by Google, which has probably billions of images. Yeah? You need to assume the attacker has a data set that also have the similar modality as Google data set, which is too strong assumption. So can we actually get rid of this same assumption, the same distribution assumption? Turns out we can, and our solution is also very easy, fairly easy. So what we do is the following, which all I did, so our initial, attack 1, the result is we're using the same distribution. Yeah, so target model is the image. I also have a similar types of image. Now what we do is we are using a completely different data set locally to train our shadow model. For example, target model can be image data set. Our shadow model can be trained on a natural language processing data set. Yeah. So other parts stay exactly the same. Other parts stay exactly the same. I only change my shadow data set to a completely different data set, and then I do the same attack. Okay. Before we give some more explanation of why this attack can work. Let's see the experiment result. Again, membership inference. And that is on these 2 matrices, the diagonal is attack 1's result. That is the shadow data set and target data set come from the same distribution. Okay? And so when the values of the diagonal are the transferring result. For example, let's see, you can see on the precision side, if we're using Sapphire 100 to attack a news data set, Sapphire 100 is the image data set, news data set is actually a natural language processing data set. You can also achieve pretty good result, 0.89 precision and 0.88 recall, yeah? Which actually is also similar to the values, or even a little bit higher to the values on the diagonal. So which means in many cases, our transferring attack or this attack 2 can work. Now let's dive into a little bit more detail to see why this attack can work. Recall one thing: the input of the attack model is not the image or the text itself. Is you need to throw the image or the text to the shadow model or target model. You get the prediction confidence. You get the posterior, and the posterior is the input to the attack model. On this left figure, on this slides, I have the TSNE dimension reduction method for the input to the attack model for Sapphire 100 and news. Yeah, as I said, the input to the attack model is the top 3 posteriors. Now I'm making it to 2 dimension with TSNE. Here, the blue circle is the members for CISPA 100 dataset, and the red square is non-members for CISPA 100. Okay, so which means, let's say, if you are using CISPA 100 as a shadow dataset, yeah, then you can easily train an attack model to separate member and non-member of CISPA. Meanwhile, also notice that the members and non-members for the news dataset also, lies in the similar region as the CISPA's member and non-member, respectively. So what this means is, if I'm able to learn local classifiers that can separate members of CISPA and member and non-member of CISPA clearly, this decision boundary, this classifier can automatically or can easily be carried or extended or transferred to separate the news member and non-member. Yeah. So what I mean here, so what's the general conclusion here? In this attack, we didn't actually transfer the dataset because this dataset, news dataset, and the CISPA 100 dataset are completely different dataset. Yeah, news is just a bunch of strings, and the CISPA is just a bunch of images. We didn't transfer dataset to make this attack. We basically transfer the overfitting behavior of the models. So if the shadow model overfitted, and if the target model is also overfitted, they are overfitted to their member samples in a similar way. That's why the attack 2 can work. Okay. By the way, so if you have any questions, feel free to interrupt me at any moment of the talk. Yeah? So I'm not sure I lost the error or it's just like something else. Yeah, if you have any questions, just let me know. Great. So this is attack 2. For attack 3, what we did is, as I mentioned before, the reason membership inference can work is because the so-called overfitting. Yeah? For attack 3, we can see, can we directly information to do membership inference? To this, it's even simpler. So this is attack 2 on the slides. For attack 3, we just don't do anything over the shadow models or attack model. All we do is we get the image, we throw to the target model, we get the posterior and use the posterior, and then we find the threshold on the largest posterior, on the largest value of the posterior. Let's see if my threshold is 0.7 and largest posterior is 0.8. So 0.8 is bigger than 0.7. So I say, okay, this is the member. That's it. Yeah, that's how this attack 3 works. Because as I mentioned, overfitting is one of the real reasons, fundamental reasons that membership inference can work, or you are able to tell member and non-member apart. So let's try to wrap it up for this this relatively old work on our membership inference attack. We have discussed 3 different adversaries. Yeah, adversary 1, 2, 3. Adversary 1 already has a less assumption compared to the original attack. Adversary 2 has even lesser assumption. Adversary 3 basically has the minimal assumption for the attacker. And the left figure is the precision, the right figure is the recall of the attack. You can see attack 1 and 2 perform similarly. Attack 3 seems a bit weak on precision, but has a quite high recall. So if you further tweak the threshold of attack 3, you should be able to achieve similar results among these 3 attacks. And as I recall, as I mentioned before, so attack 3 has a minimal assumption, but however still achieve similar result as a more complicated attack like adversary 1. This means membership inference attack can be performed in a very relaxed setting. In another way, membership inference can cause more stress than you thought. Okay, this is our membership inference attack paper by NDSS 19. And now I will talk about our newest discovery regarding membership inference domain. So all the previous attacks, not only our attack, but also other people's attack in this domain, there's one certain assumption, that is the target model will give you the posterior for the target image. So you can use the posterior, 80% panda, 10% dog, 10% cat, this posterior probability to make a judgment on membership inference. But in reality, or in many commercial machine learning applications, the machine learning model normally will only give you a label. Yeah, instead of telling you 80% is panda, will tell you, okay, this is just a panda. So previously, people thought if you do this, this is a quite solid defense against membership inference attack. Because if you only tell me this is the panda, it's hard for me to actually judge whether this is a member or not. Yeah. But however, in our newest attack, we show that even in that case, membership inference is also possible. So this is our paper that will be presented in CCS in 3 weeks, I guess. So how we do this? Actually, we propose 2 attacks. The first one is called transfer-based attack. So all we did is we first assume the attacker has a local data set. You can call it a with, and then attacker always have a target model in a black box setting. A target model will always give you the label. Yeah, but remember here is a label only attack. So we do not assume that target model will give you posteriors, but at least target model will give you labels. So you first throw your local data set to the target model to let the target model as the labeling machine to label all your local data set. Once your local data set is fully labeled, you split it by 2, training and testing. And then you use the training to train one shadow model. This looks exactly same as our attack 1 we mentioned in previous papers. Okay, so now I have one shadow model, I can train the attack model. My attack model here, my attack model input is still the largest 3 posteriors. It's still the largest 3 posteriors, yeah? Not the label itself, because why I have that posterior now? Because shadow model is trained by myself. I can control everything, and I can let the shadow model give me anything I want. Okay, so this I train the attack model. To do the attack, remember in the end, my goal here is still want to know whether this panda image is a member or not. So all I need to do here is I get a panda image. Note here, I do not throw this target sample to the target model, but I throw it to the shadow model. And of course, shadow model will give me posteriors, and I throw this posterior to the attack model. Attack model will give me the result whether this is a member or not. So here, notice one thing, the shadow model here never train, shadow model's training data set does not contain this target sample at all, which means this target sample is never a member of the shadow model. But however, we build a connection between target model and shadow model. Yeah, this connection is built by this labeling process of the target model. Yeah, because you use the data set to train the shadow model, see the data set label coming from target model. If the labeling is good enough, your data set here observed enough information from target model. So which means the shadow model will be more similar to target model. Which also means if this image is part of is a member of the shadow target model, and target model is so similar to the shadow model, also feel like this is part of the member, which allows my attack model to judge this actually is a member of the target model. This is our transfer-based attack. We also have a second attack, that is adversary example-based attack or perturbation-based attack. I'm also sure that many of you guys have heard about the adversary examples. Adversary example actually is, as I said, it's a default security attack against machine learning models. So what you do here is you have a sample, you search the target model, you get a panda. So if you do adversary example, you just add some human imperceptible noise on the image. For us, these 2 images still look the same, but however, this the noise, the image will make the model judge this is not panda, but this is a cat. Okay, this is the adversary example. How do we use the adversary example to manage the inference? Here we have a central assumption. So if a sample itself is a member, then the adversarial perturbation, which means the magnitude of the noise that you add to the image, is larger than for non-members. Because if you are a member, it is, or in another way, so if you are a member, it is harder for adversarial example attacks to perturb the prediction for this member sample compared to a non-member sample. That is the central assumption. Okay, so with these 2 approaches, these 2 approaches are independent, yeah, so they're not do it together. The independent approach, actually we are able to achieve pretty good for membership inference. Yeah, in many cases, so I don't have the time to go into detail of the experiment result here, but just remember one thing. So in this sense, even the target model will only give you a label, we are still able to do membership inference attack. Okay, so that's the thing. And the third thing, I will go very quickly regarding using management for other interesting attack. We heard about the GDPR. Also, GDPR. So one of the major notions inside is called the right to be forgotten. Yeah, and right to be forgotten in the machine learning setting translated to a notion called machine unlearning. So what this means is, let's say, if today Google uses all of us data to train a model, and if us have the right to tell Google remove my data from your model. Okay, and how Google does is, let's say, if this red hair guy asks the target model, say, remove my data, and then the target model will just remove its data and train the model from scratch. Yeah, that's the most straightforward way or legitimate way for doing machine learning. And of course, the goal of here for machine learning is to protect people's privacy, right? Because the person asked the model to delete my data to protect my privacy. But however, we find out that actually you could use this artifact of machine learning or some extra signal provided by machine learning to leak extra information that was not leaked before. So what I mean by that, suppose originally you have a target model, yeah, but however, this target model is quite well generalized. So machine inference doesn't work well. So if you are just using the original method, as I mentioned before in the previous part of the talk, if you just do a machine inference to see whether this red hair guy's data is in the target model, you may get a very average posterior. And this average posterior will not tell you, confidently that this person is a member. Okay, so which means the original machine inference on the original model somehow failed. But now this person is deleted. So you use this person again to query the unlearned model. Yeah, the unlearned model will of course give you a different posterior because your model is already different. You actually what you could do is you could use the posterior difference of the same person's data on the two versions of the model to actually build a tech model to more accurately infer, or at least the tech model is more confident that this person is part of the target model, of the original target model. Even though which means if you do not do machine learning, your membership privacy is pretty good. But however, if after you did machine learning, your privacy is actually more jeopardized. Yeah, that's actually another paper that we will present in CCS 2021. As I said, it probably will happen in 3 months. 3 weeks. Yeah. Okay, so that's basically it for the membership inference part. Any questions so far? Okay, so let's continue. Yeah? So now let's talk about another thing called data reconstruction in online learning. I need to probably speed up a bit. Machine learning models, the reason machine learning models achieve good results, as I mentioned in the very beginning of this talk, is because we have a lot of new data generated every millisecond. Yeah? So what this means is that once a powerful model is trained, you should not just leave the model there and let it be used, because no matter how powerful your model is, probably in 7 days, your model is already outdated. This is because your model didn't observe any data that happened during the past 7 days, or past 1 day, or past 24 hours, or 2 hours, etc. In consequence, to deal with this, in machine learning communities, there's a thing called online learning. So what online learning is, you have a model trained and can use it, but after a certain period of time, you just by getting the new data to fine-tune your current model. In that sense, of course, your fine-tune depends on many different paradigms. You can use less number of epochs to fine-tune it, etc. But after you fine-tune the model, your model indeed observes new information of the data. Yeah, the information of the new data. In that sense, your model is updated, and we assume that in this way your model is able to handle all kinds of data. This also means machine learning is a continuous process. It will never end if you want to deploy a machine learning classifier in commercial applications. This is good in the sense, however, we are wondering whether this can constitute a new attack surface. So what do I mean by that? So suppose today I train a model, and then I use one image. Someone train a model. I use one image to query the model. the target image. Let's see, tonight, this company will get some new data set to update model. Tomorrow morning, if the attacker or if I use the exact same image as yesterday to query target model, I will definitely get a different posterior because my target model is updated. And my target model is updated because I'm using this new data set, which means for same image, two versions of the model, I will have different result. And this different result is only caused by the data set that is used to update the target model. So our research question here in general is, can we actually use this posterior difference to infer the information of the data set used to update the model? This is our actual paper published last year at USENIX called Update Stick. Yeah, so in general, we build the general attack pipeline. We have a target model, and then we assume that our adversary have a probing data set. This probing data contains, let's say, 100 images. That's just now for talking about the image classifier. Our probing set has 100 images, and then I'm using my probing set to query the target model. I will get 100 posteriors. Yeah, I will get 100 posteriors. Suppose my target model now is updated with a so-called updating set. And then next time, once my target model is updated, the adversary use the same probing set to query target model. We'll get another 100 posteriors. And these two 100 posteriors are different because your model is updated. Then I can simply calculate this big posterior difference among these 100 posteriors. Yeah, then I can get a huge posterior difference. Once I have this big posterior difference, I can build something called the encoder to encode the posterior difference to a lower dimension. And then I can, depends on what attack I'm aiming for, so I can decode it to do 4 different categories. So this is our general attack pipeline. Yeah, this is our general attack model pipeline. Of course, today I don't have the time to talk about. I will talk about probably 1 or 2 of them. But before we go into details, I will talk about what is the encoder here. So the encoder here is actually very, very simple. So posterior difference is a vector. You are just using a multi-layer perceptron to reduce it to a latent vector. That's called an encoder. For the decoder, depends on different attacks. We have different decoders. Okay, and also before I introduce what the decoder is for different attacks, I will also tell you how do we train the attack model. Again, we rely on a notion called shadow model. We assume the attacker has a shadow model, and the attacker can also manually or artificially create a n updating set. And then with the n updating set, I can get n shadow updated model. Okay? And then attacker, remember, has a probing data set. That can be, let's say, 100 images. I throw these 100 images to the shadow model, and the first version of the shadow updating set, I will get the first posterior. If I throw the probing set to the last version of the shadow data set, I can get the last posterior difference. So what I'm doing here, again, is trying to build the data set to train my attack model. Because eventually, the input for my attack model is posterior difference. And the ground truth to train my attack model is the Y side, which is the information of the updating set. So with this X and Y for different attacks, we can extract different information from Y, so we can get different attack model result. So I definitely have no time to go for this. Now let's go to one of the most complicated attack we did in this paper, called the multi-sample reconstruction. So here, our goal here is to reconstruct the updating set. Yeah, so to construct each sample that is used to update the target model. Here, our reconstruction is based on a general, design. A general philosophy that is distribution to samples. So our goal here is the attacker first to learn the distribution of the updating set. Once the attacker has the distribution, you can keep on sampling from this distribution. You get a lot of samples, and you do some post-processing like clustering to generate, the exact updating set. So nowadays, when people are talking about, I'm learning a distribution, the first thing you have in mind or should come to your mind is so-called generative adversarial networks. Generative adversarial networks. So that's what we actually do here, but we cannot just use the original, the original GAN, because it does not necessarily fit our setting. So what we do here is we propose a new GAN called the CBM-GAN. In this slide, I will first introduce what is a normal GAN. So normal GAN is, if you guys are familiar here with GANs, I will go a bit faster. Normal GAN is, let's say, composed of two neural networks. One is called generator, the other is called discriminator. The generator's input is just a noise. It's just a Gaussian noise, 128 dimension, for example. You throw the noise to generator will generate an image. Yeah? And once the generator generates the image during the training process, the image will be thrown to the discriminator. The discriminator's goal is to try to judge that the image generated from the generator is a fake image. You see, the goal of the GAN thing, the generator, is I try to generate as real image, as images as real as possible. On the other hand, discriminator try to be as powerful as possible to judge whether an image you give to me is a real image or fake image. So in this sense, generator and discriminator are actually a competing role. So you can actually train this in a game theoretical way, and in the end, two models will converge. And then your generator will be able to learn a distribution. And then whenever you give whatever noise to the generator will give you whatever image. Yeah, some real images. This is the original GAN. So what we do here, remember, our goal here, our attacker, at least our attack's input is the posterior difference. Yeah, because the goal here is I want to use the generator to learn the distribution of the entire model. I want to use the generator to learn the distribution of the updating set. So what we do is we introduce CBM-GAN with the new component. So again, we have the generator, we have discriminator. We also added the encoder, which is from posterior difference to a lower dimension, and concatenate the latent vector together with noise as the input to generator. This gave the signal to connect the generator to updating. It's solely reflected on the posterior differences. And then we propose a new loss function for optimizing the generator. For this optimization function, the red part, if you only look at the red part, which is log dx, the dx head, that is just the classical, loss function for the generator for the original GAN. The left part, which we call it best match loss, is what we add. So actually, this best match loss actually is very simple. It basically says for every sample in the updating set, actually, to be more precise, for every sample in the shadow updating set, let it learn an image x hat to be as close as the sample in the shadow updating set. Yeah, and then I sum everything together, which allows my generator to able to learn the distribution or to learn each sample, which in the updating set, which also gives it the ability to learn the general distribution of the updating set. So that's what this CBM-GAN is, and the major part here is the best match loss, which is also actually quite simple. We have some quantitative result, but it's rather to show you some quantitative example. It's probably easier. So assume that my current model here are trained on a famous data set called MNIST. Yeah. And suppose my model is updated with 100 MNIST images. On this slide, I have 200 images. I have 200 digits. All the first column is the original sample that is used to update the model. All the red column are samples that I generated with my attack model. You can see in many cases, actually in most cases, my generated samples are very close to what the real sample is. This means our data reconstruction with the CBM-GAN style works At least on this simple data set. At least on this simple data set. Okay, so that's basically it for the second part of the talk. Any questions? Graph neural networks. No, it's definitely one of the most popular topics in machine learning. The difference between graph neural networks and the normal neural networks is that graph neural networks directly handle the. Sorry, can someone turn off your microphone? I hear some noise, I think. Okay, great. Anyway, so graph. I think some. Okay, great. So graph neural networks. The difference is graph neural networks is designed to automatically handle the graph style data, like social networks. For example, left is the traditional DNN, and the right is the so-called GNN. So you're not only think about consider each node features, but also the structure of among different nodes. Okay, great. So that's what GNN is. And there are multiple, different kinds of GNNs. The most classical one is called transductive GNN. In that sense, when you train your GNN, you assume you have the whole graph. You have every node feature. The only thing missing is the green, this blue and red nodes label. In that sense, it's a bit like semi-supervised learning. You know the features of the testing set, but you just don't know the label. But you consider all of them together to train a GNN model. Once your GNN model is trained, to make the prediction on the label of the blue node and red node, all we need to do is just throw the ID of the blue node, because the blue node feature is already used to train the GNN. Yeah. So I just need to throw the ID to GNN. GNN will tell me, okay, 70 pad. In case if I want to know the GNN red node, so I just throw the ID of the GNN and I get the posterior. I think that differentiate GNN from normal other NNs. It contains the graph information. Information is used, and of course, graph information in many cases is very valuable, and GNN find the right way to interpret it from the data. This also means the data, the graph is quite, in many cases, quite. Our question here is actually quite simple. So if I just query interface, am I able to judge the blue node and red node are connected or not? In that sense, or in general, so if I give you a black box GNN, am I able to reconstruct that is used to train GNN? Because the information is important, and if you are able to steal the graph information, you will proceed. You will make the model more private. This is actually to 1 month ago at USENIX system. So at first time I only have 7 minutes left, but here in this paper we did a general attack taxonomy. We consider attacker cannot have 3 sets of information. The first set is all the node features of the target model. Yeah? The target model training data set. Second part is I assume I know the partial part of the graph of the target model training data set. The third one is I assume I have a shadow graph. As I said, so this is the 3D knowledge. Attacker can have it, or which is binary choice. At the end, I will get 8 different scenarios. And for 8 different scenarios of the attacker, we propose eight different kind of attacks. And I'm introduce the first attack here, so which is simple and the most probably more difficult one. Anything all attacker can do is you use the blue node or red node to query the GNN model, and you get that it. Yeah. In that sense, I'm able to judge whether blue and red node are connected or not. So it turns out is you can. Yeah. So all you do is very simple, because the information you can use is very minimal. Yeah. In that sense, your attack can be very simple. All you do is you just calculate a cosine distance or cosine similarity between these 2 nodes posteriors. If your similarity is higher, then you assume they are more likely to be connected. That's it. Yeah, that's how this attack works. You could actually, in a next attack, you can assume that the partial graph is available. In that sense, you can use the same information, but since you know some real, you can actually train a classifier to judge whether two nodes are connected or not with the same set. Yeah, but sorry. So this is a very simple introduction about this paper. More detail can be found here. But basically, the general intuition for our attack is if two nodes are graph, more likely to are similar. In that sense, this can be used to infer these two nodes are linked, even though the attacker does not know. Attack 7 in general has the most number of information, most resources, and attack 0 has basically nothing, as I showed before. So we can see that, of course, more knowledge attacker has, better attack performance. More importantly, we have 3 dimensions of different attacker knowledges. Attacker knowledge, the partial graph actually is the most useful one from this figure. Yeah? And the shadow data set is basically not really useful, or in some cases we use this. And more importantly, all our attacks in many cases on different data sets actually perform better than the traditional link prediction attack, which means you just judge whether two nodes are linked or not from data set itself without involving GNN. What this means is GNN indeed leaks extra information leaks extra private information that was not supposed to leak by GNN itself. I think that we are actually recently also do many other attacks against GNNs. For example, another paper we will just got accepted at USENIX Security 2022 is called Inference attack against graph neural networks, which is like an actual inference attack. This paper, as well as the machine inference paper against GNNs, are both on my website, which are both on archive, I think. Yeah, both on archive, I guess. If you have, if you're more interested in, understanding or try to study privacy risks of GNN models, yeah, feel free to read the paper. And if you have any questions, feel free to reach out. I think that's it for my case. So in the end, I would like to thank all my collaborators for their contributions. What I'm talking about today here, it's not possible. I think that's it. So I have 2 minutes left. So please, if you have any questions, so please go ahead.